Hello everyone. Today I want to present our work MIXIQ, rethinking ultra-low power receiver design for next generation on-body applications. A significant body of research in wireless communication in recent years has focused on the development of ultra-low power backscatter radios that can operate on extremely tiny power budgets while being compatible with commodity radios such as Wi-Fi, LoRa, BLE, and Zigbee. Of these, Wi-Fi compatibility is perhaps the most important given the widespread coverage offered by Wi-Fi. Most of these efforts, however, focus on enhancing upstream communication with few, if any, hardware-level enhancements to the tag-side receiver for downstream communication. For example, while the Wi-Fi backscatter uplink has evolved over the years to achieve impressive bit rates of several tens of megabits per second, downlink performance has largely remained stagnant. The reason is that it is relatively easy to prototype upstream communication with elements like RF switches, transistors, and simple circuits. As a result, much of the recent systems activity in backscatter has focused on the upstream communication with limited enhancements to the receiver. In comparison, it is harder to prototype new designs of ultra-low power receivers, so most backscatter efforts use the same vanilla envelope detector circuit that is used in standard UHF RFID tags. The optimizations at the receiver are limited to reverse engineering the Wi-Fi packet to emulate an on-off-key signal that is decodable by the detector. While several efforts have focused on leveraging the growing uplink bandwidth of Wi-Fi backscatter to transmit richer sensor data to the base station, for example, streaming video and audio and sensor data in real time, there has been essentially no work on applications like hearables that are dominated by downlink data transfer. Typical methods like on-off-key emulation that show how the protocol works with vanilla envelope detector are inefficient and have poor spectral efficiency. Let me briefly explain what I mean by a vanilla envelope detector. A vanilla envelope detector consists of an RF rectifier circuit followed by an ultra-low power voltage comparator. When an on-off-key signal arrives at the antenna, the rectifier converts the RF signal to an amplitude-varying LF signal. The comparator then generates zeros and ones based on whether the amplitude is below or above the threshold. Such a circuit is very energy efficient and also easy to assemble using one of the many RF Schottky diodes and ultra-low power comparators in the market. The vanilla envelope detector is also simple to interface with Wi-Fi by manipulating the payload of a packet to mimic an on-off-key signal. However, its sensitivity is only around -20 to -30 dBm. When prototyped using off-the-shelf components, which makes it impractical for many interesting applications. In many on-body applications, the RSSI can be as low as -50 dBm, which is far below the sensitivity of the detector. In addition, since the envelope detector is only sensitive to the power of the received RF signal, it has poor spectral efficiency. The entire band needs to be free during the time the tag is receiving data from the transmitter, and no more than 1 bit can be sent to the tag during each symbol time. We present MIXIQ, a new ultra-low power Wi-Fi receiver design that is easy to prototype using off-the-shelf components. MIXIQ transforms the passive envelope detector to behave like an advanced receiver with high sensitivity and the ability to decode complex, high data rate signals, while also keeping its energy footprint in the microwatt regime, even when it is implemented with off-the-shelf components. At a high level, MIXIQ works as follows. First, we transmit a data plus helper signal from the Wi-Fi device. When such a helper plus data signal passes through an envelope detector, the latter's nonlinearity allows for the conversion of the incoming data signal to a much lower frequency That is the difference of the two carrier frequencies, referred to as the delta signal. Thus, the phase and amplitude of the incoming UHF data signal are transferred to sub-megahertz frequencies without any additional energy cost. Second, MIXIQ leverages the very low frequency nature of the delta signal to design a highly power efficient demodulation pipeline that not only gets rid of the undesired intermodulation signals, but also increases A, sensitivity through voltage amplification that leverages high impedance analog components at micropower, and B, spectral efficiency through a fully digital micropower IQ demodulation. Realizing MIXIQ's architecture in practice necessitates addressing several technical challenges. First, the helper signal needs to be generated in the same standard Wi-Fi device that is generating the data signal, and it should be sufficiently separated in the frequency domain. A separate device for helper signal generation makes the system less practical. Second, increasing the channel bandwidth contributes to larger data rates, but results in severe degradation of receive sensitivity. Higher bandwidth requires a higher delta F. However, increasing delta F has two detrimental effects on sensitivity. One, the down conversion ratio, i.e. the ratio between the amplitude of the down converted signal at the output of the rectifier and RF input power, rapidly decreases with higher delta F. Two, gains achieved by micropower amplifiers at higher delta Fs are lower. So migrating from sub-megahertz to several megahertz for obtaining higher bandwidth can compromise the sensitivity by as much as 30 dB. Third, the modulation of complex waveforms requires us to track the abrupt changes in the amplitude and phase of the down-converted data signal without introducing any distortion. However, achieving this goal with passive and low power components is challenging. If the filter has a wide passband, it cannot completely filter out the unwanted terms. On the other hand, a narrow passband filter makes the filter simple but unable to track the rapid changes in amplitude and phase. In a sense, designing a baseband for our receiver is highly non-trivial. We present MIXIQ's transmitter design to tackle these challenges. MIXIQ leverages Wi-Fi 6 or 802.11a OFDMA to operate on a much smaller bandwidth called resource unit. This has two key benefits. First, increased sensitivity from improved down conversion ratio and ultra-low power amplifier gains. Second, increased data rate by allowing for fully digital IQ demodulation of complex high-rate modulations using ultra-low power, high-resolution ADCs. MIXIQ leverages the smallest resource unit of 2.2 megahertz, which consists of two pilot tones. Given that the pilot tones cannot be suppressed, MIXIQ employs one of the pilot tones as its helper signal. Numerical analysis shows that more than 200 kilohertz frequency difference is necessary for enabling high order modulation. MIXIQ uses only the three data subcarriers on the left side of the left pilot tone. The reason is that the rest of the subcarriers either overlap in frequency after down conversion or are too far from the helper tone. MIXIQ nullifies the unwanted data subcarriers by giving them the smallest amplitude. Although the residual terms appear as transmitter noise, MIXIQ is able to reduce the total power of these residual terms after demodulation to 35 dB below the power of the data by searching for the best combination of the low amplitude symbols. We now describe MIXIQ's RX baseband pipeline. Unlike UHF frequencies, where it is necessary to keep input and output impedances matched to 50 ohm, at sub-megahertz frequencies, we can have stable voltage amplifiers with very high input and output impedances. MIXIQ employs a voltage amplifier design consisting of two common emitter stages that can significantly amplify the output of the rectifier at micro power consumption. The overall gain of MIXIQ's two-stage amplifier is about 57 dB when the amplifier is placed between the rectifier and the next stage in the pipeline. MIXIQ can acquire the whole down-converted delta waveform with just a sampling rate of 1 megasamples per second. Thus, a reasonably high-resolution ADC can be employed to convert the signal to the digital domain at very low power. Therefore, MIXIQ digitally multiplies the samples of the delta signal with the locally stored cosine and sine waveforms, thereby allowing it to completely bypass the challenges with analog filters. MIXIQ employs an ultra-low power CPLD for implementing the logic. CPLDs are programmable logic ICs that can be found at low energy footprints. We have built a PCB prototype of our MIXIQ receiver with off-the-shelf components. Also, we implement the Wi-Fi signaling scheme of MIXIQ on both the commercially available Wi-Fi 6 chipset running OpenWRT, as well as in MATLAB's WLAN toolbox. The MATLAB emulation allows us to evaluate the effect of hardware imperfections and to ensure that the result can generalize to any 802.11ax implementation. Now we outline a summary of MIXIQ evaluations. The overall power consumption of our PCB-based implementation is about 360 microwatts, while achieving a 1.1 megabits per second bitrate. Thus, we see that MIXIQ provides much improved performance while sacrificing a small amount of energy footprint. Also, it can be seen that to achieve near zero bit error rate, vanilla envelope detector needs an RSS greater than minus 26 dBm, whereas MIXIQ can work at RSS as low as minus 52 dBm. In other words, MIXIQ improves the receive sensitivity by more than 25 dB over that of vanilla envelope detector. We also conducted a range experiment in a 24-meter long hallway. The vanilla envelope detector can successfully decode at only 2 to 3 meters away from the Wi-Fi TX device in line of sight, whereas MIXIQ is able to do so across all the distances, which means at least 10 times higher range than vanilla envelope detector. Finally, we show the benefit of a better receiver using a novel Wi-Fi based VoIP or audio streaming prototype that uses MIXIQ to achieve better performance. We consider a Wi-Fi device that is transmitting the VoIP signal with an audio quality of 128 kbps at 17 dBm. Also, we implemented a digital audio player that mimics a simple version of a hearable. MIXIQ has a good MOS score at up to 7 meter, and the quality slightly degrades between 7 and 10 to 11 meters. On the other hand, the vanilla envelope detector fails to deliver fair quality audio even at 1 meter.